Hello, everyone, and welcome to this topic of regularization. So, we'll see what regularization is and why it is important. Uh, this is basically the model optimization strategy. Okay, there are many strategies in machine learning which are used to reduce the test error. All right, because that is what really matters. Okay, even if it increases the training error. All right, because training is when done in a lab setup. All right, and eventually what you're going to do is you're going to deploy your model, and that model has to perform on real life, real time um, instances. Okay, real time data. So so these strategies which will reduce our test error even at the expense of increasing the training error are collectively known as regularization strategies. Okay, so any modification we make in the algorithm, learning algorithm, that is intended to reduce its generalization error, but it's not its training error. Okay, is something called as regularization. All right, and there are many regularization strategies. Some put extra constraints on machine learning models, and the others add the extra terms in objective function. Okay, let's see. So these are the three scenarios after which, if your model is trained, all right, and one of these three scenarios will happen. That is, the model will exclude the true data generating process, that is underfitting. Okay, the true data generating process is basically the training data. Okay, so basically what does it means? It means is that the model is performing poorly on the data that it was trained on. All right, and that is very bad news. Okay, the next is this C, problem C, where it included the generating process, but also many other possibilities of the generating process, which is called as overfitting. So basically, in this scenario, what happens is, in overfitting scenario, what happens is our model learns the data that it was given so well that it also learns the noise along with it. Noise is basically the data that is an exception. Okay, and to have a very good model, data that may or may not be encountered anytime soon is not a great idea. Okay, you don't want the model to remember something which could be an error. All right, so that is the state of overfitting, and the opposite is the underfitting, which in which it does not even perform well on the data that it was trained on. Okay, and the third scenario which we actually want is it matches the true data generating process. Okay, so it fits with some 80 to 90% accuracy is always our goal. We don't want 100% accuracy, but the data generating process, which is the training process. Okay, if we could fit, that is, we could achieve the uh, accuracy of say 80 to 90%, that's a very good accuracy. All right, so the goal of regularization is to take, now what is regularization? The goal of regularization is to take a model from the third regime into the second regime. So overfitting models, if our data is rote learning, doing rote learning of the data, then we have to take it from overfitting to a normal state. Okay, where it is not uh, overfitting, but it's a acceptable ratio. All right, so how do we accomplish this thing? There are penalties associated with it, with uh, we can have penalties associated with updating the weights, okay, or calculating the losses. And what are the penalties? We'll see it over here. The penalties are uh, L1 or lasso, okay, in which the error plus a lambda, the error plus lambda into summation of wi, where lambda basically is a learning rate and summation of wi is summation of the absolute weights, okay. So that could be a penalty that is introduced in uh, the loss function, and that is called as the lasso penalty. All right. We also have a linear regression model named and after this selection of loss function. It is called as lasso regression. So lasso regression method. So anyone with background of machine learning might recall that there was a linear lasso regression algorithm in machine learning, and that algorithm has this loss function associated with it. Moving on, we have ridge regression or ridge penalty. Okay, so penalty is loss function is equal to error plus lambda into summation of wi square. Okay, so the squared of weights is the penalty over here. Next, we have elastic net, which basically combines L1 and L2. So we have L1 over here and L2 over here along with the error, and that is our uh, penalty. Okay, so when you introduce this penalties into the loss function and then calculate uh, your next value, that is what is called as lasso or ridge or elastic net uh, errors. All right, or basically your that is those are the penalties that you could use. Okay, next we could use bagging, some a bagging called as bagging, sorry, a process called as bagging or other ensemble methods. Okay, so bagging is where you have, say, this data set, the original data set, and multiple occurrences of this digits. Okay, so let's assume that we have multiple occurrences of 9, 6 and 8 uh, in our data set. Okay, and what we do is we divide it into a number of different samples, subsets. Okay, so suppose there is a subset which contains two eights and one six. Okay, and we give it to our machine learning, or sorry, not machine learning, our deep learning neural network. Okay, and we ask it to uh, we basically train it, right? So since uh, the machine learning, the deep learning data, uh, the neurons learn the pattern in the data. Okay, it might so happen that uh, the differentiation between 6 and 8 for that deep learning model could be if the if there's a loop, if there's a zero, or if there is this circular shape on the top, then it's a 8, occurrence of 8, otherwise it is a 6. Okay, consider the second scenario where you give two instances of 9 and one instance of 8. Here the model could learn the opposite way, that is, if there is a circle on the bottom, then it could mean that it is an 8, otherwise it is a 9. All right, now in both these cases, all right, in both these cases we have different outputs, right? So what we can do is, in this way, what we if you want to avoid over learning or overfitting of data, you can divide this your data, entire data, into different samples, and they could come up with their own assumptions. Okay, now we intuitively we know that uh, 8 is occurrence of both, right? The above circle as well as the below circle. Okay, but if you do this on multiple with along with multiple samples, you create different subsets. Okay, and those subsets of data are further passed to different neural networks, and those neural networks come up with their own answers. What we could have is, in the end, we could have, uh, if it is a classification problem like we have over here, we could have a simple majority. All right, a simple majority of vote, and that could serve as a purpose. All right, or if it is a regression problem, then we could have an average. Okay, an average of all the values. Okay, since regression is continuous and classification is discrete values. Okay, next we come to sparse representations. So we can also achieve our regularization. Okay, regularization is converting your model from overfitting to a normal model. Okay, so we can have that done even by sparse representations. Sparse representation is, if you observe this data, all right, uh, the there are many zeros included uh, in this parameters. Okay, and parameters are basically biases and weights. All right, and the other way is, we could use sparse we could pass our x as sparse. Okay, we could make our x as sparse and keep the weights and biases as same. Okay, sparse network basically means that you don't have all the connections of your, it's the opposite of dense network. Okay, so dense network basically means that in your current layer, or if you consider any layer, okay, all the connections of that layer are made to the previous sorry the following uh, layer. Okay, so each neuron in the uh, nth layer is connected to each neuron in the n plus 1 layer. That is dense network, and opposite of that is not all are connected. So basically, you either introduce zeros in your weights and biases, or you introduce zeros in your x's. Okay, that is sparse representation. Dropout is the same uh, concept. Basically, what you do is you delete some of the connections. Okay, as you can see over here, this is the dense network, and these are sparsely connected. Okay, what basically you do is ensemble consists of all sub networks. Okay, that can be formed by removing non-output units. Okay, so other than the input units, you can uh, remove all the non-output units, and a large number of models can be formed. Okay, uh, variants are binary mask and sparse mask, uh, and dropout boosting. Parameter sharing happens over here. So parameter sharing is basically, if you do have to do one calculation many number of times, then you can just simply share that with the other neuron. All right. So dropout is one way. Next is early stopping. Early stopping is when, while training large models with sufficient training representational capacity to overfit the training error, uh, decreases steadily, but validation set error begins to rise. So basically, what it means is, when your training error, okay, the one in blue line, all right, it decreases, but the validation error either increases or remains the same. All right, And why is validation error? Okay, what is validation error first of all? So after every training set, we evaluate the losses, right? And that tell us how our error, our model is fitting, right? So what we can do is we can have a separate validation loss calculated after the training, okay, after each training, and that is done on the data which is not a part of training data, okay, that is called as validation data. This is different from the testing data, because testing data is done at the end of training process. The entire process is finished and then you have your testing data, whereas validation data is after every epoch, or maybe after every simple run, okay, after every iteration you could have a validation error or validation loss calculated, okay. So when we are at a point where our validation error either increases or remains the same, and our test error uh, is reducing, okay, so at that point we have to make a decision that we have to stop the training process, okay. So when we stop this training process, how can we achieve that? Well, we store the copies of parameters, return to the best parameters, okay, the pre-specified number of iterations, after which we will see, uh, if, say for example, at 100th iteration, after 100th iteration, we go up to 50 iterations, and we see that the error has either validation error, okay, more specifically validation error has either increased or remained the same. Then we go to the 100th, we stop the training process and we go to the 100th iteration, and we take those parameters as the best parameters, okay. So as I said, there are pre-specified number of iterations. It is popular and effective, and because it is very popular because it is effective and simple, okay. It's the same thing written. Now, what if the data that you're working on is not textual data? It is image data? All right. So how do we introduce regularization in image data? Right. So for that we have something called as data augmentation. Okay. So you modify the image somehow. All right. Modify in the sense that you could sorry you could do operations like translation, okay, translation of image, uh, training a few pixels in each direction, then convolution and pooling techniques, which we will learn later on. But simple things such as rotation, scaling, then rotating by a few uh, angles, okay. Like these operations can be performed on image data, and we basically it is one way of creating a fake data and add it to the training set, okay. I should have read this. It's a very good statement. It's a way to create fake data and add it to the training set, okay. And this is done when the amount of data is limited, okay. So obviously when you have a limited data, there's a greater chance of overfitting, because the model will recognize the will model is very likely to memorize uh, all the features of that image, okay. uh, Then there's a caution written, transformations that would change the correct class, for example, the difference between B and D, and the difference between 6 and 9. So horizontal flips of 80 degree would be catastrophic. Okay, so basically it's not always advisable, because you can see that B and D and 6 and 9 are, if you flip them by 180 degree, it would be that the classes actually change, right? So injecting noise in the input to a neural network is also seen as the form of data augmentation. Uh, in introducing noise is just it is applied to inputs, hidden inputs and outputs. The cost function analysis at local minimum. So basically, what we do is, with noise introduction, is that we uh, say blur that image, or we could have uh, a noise is basically un unwanted data. Okay, so whatever is any entry that you do in image, okay, any modification that you do to your image, which basically uh, distorts the quality of that image, is basically noise. Okay, and you have to see that your image classification is robust to this noise. Okay, then there is adversarial training. Okay, so adversarial training is such that, suppose, okay, and then we have our data, which, if you see, all the data points lie over here. All right, and if we introduce noise like it is shown over here, all right, if we introduce noise like it is shown over here, it might end up we might end up with uh, data set which is over here. Okay, and it has the same to our human eye, to a human eye it will look the same. Okay, that is, if you can see over here, there's an image of a panda. All right, and uh, what what we have done is, we have just multiplied that with a 0.007 of noise. Okay, and what happened is that data came out to be here. Okay, so basically what is happening is, if you have a data set, okay, all the vectors for this data set might lie over here. Okay, but instead, when we introduce the noise, it came over here. Okay, all came over here. Now this is our actual data, and this is the adversary. Okay, adversary is basically, in human in normal English, adversary is a villain. Okay, so what we have done is, by adding some uh, noise, all right, what we have done is, we have created an adversary which is indistinguishable for humans. Okay, so if humans, as a human, if we see over here, it is indistinguishable, but to computer it is entirely different. It is something that is entirely different. All right, and you can do this so that uh, your security of the model is not compromised. Okay, so that is the reason for adversarial training, especially linear models such as linear and logistic. Adversarial inputs are indistinguishable, as I said. It can be intentional or and risky for model. When it occurs in high dimensional data and virtual adversarial X dash to make robust models. Okay, so what you can do is, you can have this adversaries created and train your model to distinguish them from the actual. Uh, with that, we come to the end of this topic. See you in next lecture. Thank you.